Hello everyone and welcome to a new tutorial for the software package Vampire. My name is Mara and in today's video I will talk about Spin-lattice dynamic simulation. More precisely, this video will cover the following topics: why we need Spin-lattice dynamics, how are these implemented, and how do we run a Spin-lattice dynamic simulation. Before digging into the tutorial, I would like to mention that the implementation is based on this following paper, and we acknowledge funding from ACHA2 to implement the framework into Vampire. Let's make a start. To have a complete model of a magnetic system, we need to include the following subsystems: electrons, spins, and phonons. Electrons relast very fast, around 1 femtosecond, in comparison with spin and lattice. And the first assumption in a spin-lattice dynamics framework is to consider the electrons in equilibrium. Now, the relaxation of spin and lattice can be in the same order of magnitude, picoseconds, so we need to treat them self-consistently. This model is powerful because it could trace the flow of angular momentum between subsystems and could lead to better understanding of effects such as the Einstein d-Haas that appears due to angular momentum conservation. Since we include phonons, we can also understand how lattice effects affect magnetic properties such as exchange, anisotropy, switching, and so on. Phonons also contribute to the damping mechanism, so we can understand it better and model more realistically the relaxation of magnetic insulators, for example. How do we construct such a model? Let's start with the Hamiltonian, which has a magnetic part and a mechanical part. For the mechanical part, the potential and kinetic energy are included, and for the magnetic part, for the moment, we include only exchange and a coupling between lattice and spins. At the moment, the mechanical potential in Vampire is very simplistic, only a harmonic approximation, but we plan to develop different choices of potential, so it will be more realistic. Based on the Hamiltonian, we can express the forces and fields that act on each atom. To these, we add the thermal noises, which are uncorrelated in time and in space, so white noise. We use the forces and fields into the equation of motion and integrate the position and velocity of the atoms. For the integration of the spin, we use the Landau-Lifshitz-Gilbert equation that describes the damping dynamics of magnetic moment in an effective field. However, we can set the Gilbert damping to 0 and study the magnetic dynamics of a magnetic system, which is thermalized only by phonons via the spin-lattice coupling. Now let's move on to the next part of this tutorial, which is setting up simulations in Vampire. We open a terminal into the main Vampire folder that was developed from GitHub, was downloaded from GitHub. We go into the Spin-lattice branch, so git check out Spin-lattice, git branch. So here it says we are already in the Spin-lattice branch, and when we press git branch, we are here, so all's good. We can compile the code. So only the serial version is fully working. We are currently still developing the parallel one, so stay tuned for future changes. So now the code is compiling. It's compiled. So we can go to the first exercise, tutorial 1. So I have already kind of made the input files here just for the sake of the tutorial, just to be a bit easier to show you how to set up a simulation. So in the input file, we have here the first part regarding the creation of the system. So there's this is for a BCC iron. So we have a BCC crystal structure, periodic XYZ. The in cell size is 2.87 angstrom. and we have a 10 by 10 by 10 unit cell system. The material parameters are set up in this file here. We'll go there in 1 second. And we run a benchmark simulation. And what's really important for the spin lattice dynamics is to set up the integrator with this flag here, spin lattice. So the integrator for the spin lattice dynamics, it's quite different than the rest of programs, integrators which are used in Vampire. So we actually use Suzuki Trotter decomposition. So this is a symplectic integrator. It's very stable, very accurate. It conserves energy and can deal with non-commuting operators. So we need to update the position, velocity, and the spins, and these depend one on each other. So what we do, we decompose the system into separate updates, and we use this scheme where we update first the spin, then the velocity, then the position, velocity, and spin again. Now, in the case of the spin, we need to further decompose these because the spins do not commute between each other, because each spin interacts with each other via exchange. And when you update one spin, as shown here, this one depends on the effective field created by the neighboring spins. So we need to further decompose the spin system as here. So this is the current integration method implemented in Vampire under the label spin lattice. Okay, so we go back, we have set up the integrator, a benchmark simulation. Now we need to set up a few parameters for BCC iron. So we have here the cutoff for the mechanical and for the magnetic interaction. So for the mechanical interaction, we have a 7.8 angstrom cutoff. So all the forces are calculated up to this distance. And for the fields, it's 3.75 angstroms. And we may want to make sure that we calculate the exchange and all the neighbors up to that distance. So this one has been set to 3. In terms of the potential, we have here the harmonic flag. This is the only option at the moment in Vampire, but we're working to implement more choices here. And this is the spin lattice coupling, which is basically this energy term here that couples the spins to the mechanical degrees of freedom to the position. And we use a pseudo-dipolar form of the coupling as shown here. And the prefactor has this variation. It depends with 1 over distance to the 4th power. And in the code, we set up this constant here, this coupling constant. And we set that up to 0.5, which is a relatively strong couple. But for the sake of having fast simulation, fast equilibration, we set that to relatively high value. So that's the pseudo-dipolar coupling. We can also output the configuration of the atoms during the simulation time. So for this, we need a separate flag config SLD. The quantities we want to look at are the magnetization, the spin temperature, and lattice temperature for this benchmark test. Okay, now we can look on the material file for the simulation. So the first part, it's the part related to the magnetic properties, and the second to the mechanical properties. So here, sorry, it's cobalt, it should be iron. We give the Gilbert damping 0.1, the spin moment of iron, and some initial preparation direction. In this case, it's orientated along Z. Anisotropy is commented. We don't have any anisotropy here. And now the parts, the properties related to the spin lattice simulation. So we give here the mass of the atoms, which is in this unit. The exchange constant, which is in electron volts. So the exchange has this form here, implemented as here. The harmonic potential, strength in, again, electron volts, and the coupling. This is the spin lattice coupling, which is set to 0.5. So we have all the calculations, all the parameters set up. We copy the executable. Sorry, I'll just remove the old one and copy the executable from the previous file, and we can run the simulation. Okay, so this is running. In the meantime, we can do some plotting, just not kind of wait. We have seen in the input file that the first quantity is the time that follows the magnetization, spin temperature, and lattice temperature. Okay, so let's plot that with your favorite plotting tool. My case is gnuplot. Continue plot. Let's plot the spin temperature. So column 1, it's time, 2, 3, 4, it's, and 5, it's magnetization, and then 6 is lattice temperature, spin temperature, sorry. So, okay, so we have set up benchmark simulation to 10 Kelvin, and we see already that the spin temperature equilibrates to 10 Kelvin. Okay, now let's see what the lattice is doing. So we can plot the lattice temperature as well here. It's column 7 with line title TL, lattice temperature. The lattice is much slower, so it will take a bit more time to equilibrate to the same thermostat temperature. So you just need to run the simulation for a bit longer. And we can also check out the magnetization. So the length of the magnetization. So we see that we started from a saturated state, normalized to 1, and we see that after some time it starts to decrease to a smaller value corresponding to a temperature of 10 Kelvin. So it seems fine, all is fine. We can also put all these plotting commands in a file here, and you can plot automatically. Where, for example, you have the magnetization on one axis and the temperature on the second axis. So if we plot that out and we check here, so this is what the current simulation is doing. So it still has some time, so it's about 1.6 picoseconds out of 10 picoseconds. Lattice is still not equilibrated. So yeah, the final results will look something like this. So after 10 picoseconds, your results should look like here. Now, the second tutorial is about conservation of energy. So we want to make sure that our integrator conserves the energy, we don't have any energy drift. We want to decouple our spin and lattice system from their thermostat. So for that, we just simply set the damping constants to 0. So this is the spin damping and the lattice damping. So these are set to 0. This is the change we do in the material file. So now in the input file, we keep the same system as shown here. Material parameters are in this here. We use a time series program, so just integrating over 50,000 time step, spin lattice integrator, in order to start from some initial energy, so to have some initial energy deposited in the system, we can randomly displace the atoms in a sphere with a radius of 0.1 angstroms, I believe. And we also can attribute to each atom velocity in accordance with the Boltzmann distribution for 600 Kelvin. So this is this initial thermal velocity. And we can output here the energy. So we have the kinetic energy, potential, exchange, and coupling. We also have a flag for the total energy. Okay, so these are the inputs for a conservation of energy test. So we can copy the executable from the previous folder and run that. Now it's running. In the meantime, we can plot it. So if we look at the input file, we need to plot the following columns. So first this time there are 4 columns for the magnetization, 6 and 7 is the spin-lattice temperature. So from 8 will be the energies. So 8, 9, 10, 11. Okay, and 12 is the total energy. So plot that. So we plot the sum of the energies in the system. 9. Oops, sorry. Oh, okay. 8 plus 9 plus 10, 11. And the same value should be column 12. So yeah, we have, this is the variation of the total energy. You see here on the labels, the variation is really, really small. It's 10 to minus 5. The magnitude of 10 to minus 5. And we see that it oscillates around some equilibrium position. So if we wait long enough, the variation of energy, the amplitude of the energy variation should decrease, and it should stabilize to some value, and we shouldn't see any drift. So you can wait for the simulation to run longer. Here are the results for 10 picoseconds, and we see some initial variation of the energy, but then it stabilizes and it varies very little, and there's no drift in the energy. Sorry, this is energy instead of temperature. Okay, so this is the second tutorial. I'll just leave this running until we complete also the third one. So we'll move to the third tutorial, third exercise, which is magnetization versus temperature curve. Oops, sorry. So let's have a look at the input file. So we decreased here the system size is to 4 by 4 by 4 unit cells, just to make a bit the simulation faster. We specify here the program, the Curie temperature program. We keep the same integrator. These parameters are the same. We set up here the minimum maximum temperature step, and the calibration and loop time steps. So this is a relatively small number of calibration time steps, but just kind of for the sake of the exercise, we keep this relatively low. And in the case of the material file, we connect the two subsystems to a thermostat, so the damping constants are non-zero. So here the lattice spin damping is 0.5, a bit larger value than the first exercise, just to calibrate faster, and here is 0.6. And yeah, we can run this as we done before with /vampire serial. And here the simulation is already running for a while, and we can plot the quantities we're interested in. So we have outputted the temperature, magnetization, the spin-lattice temperature, and the mean magnetization length. So let's just see how the spin-lattice temperature look like. So again, GNU plot. Column 6 for the spin temperature, and then column 7 for the lattice temperature. So we see that these have not yet equilibrated very well. So in principle, we should reproduce, we should be able to get exactly the thermostat temperature, but we see that there's a couple of deviation from the blue line, which is just a linear fraction, and should show us that the two systems are well equilibrated. Okay, so if we leave this long enough to run, we should be able to obtain a result similar to this. So this is the linear function, the black line, and we see some variation of the two subsystem around the thermostat temperature. And if we plot the magnetization, the mean magnetization length, it should reproduce the well-established the curve you expect. However, just bear in mind that these values used here are very low, so you really need to increase this to 50,000 time steps to be able to get accurate results. So this was a brief tutorial on the spin-lattice dynamic simulations. All these features are in serial. However, we work to release a parallel version very soon. So you can follow the progress on GitHub and also what new features we will implement in the future. So thank you for your attention, and I hope you found it useful.